So this is joint work with Ryan Newton and Andrew Longstein at Indiana University. So nowadays, supercomputing has moved on from the era of just dense linear algebra or relatively nice unstructured meshes. And so you have a much wider variety of data-driven and highly irregular problems. And one abstraction that's important in that domain is graphs. So you might think, oh, graphs are just this esoteric thing you read about in textbooks. Well, did you use a graph algorithm today? What about this one? I mean, Google is basically a large sparse eigenvalue problem on a gigantic graph. So in a more traditional supercomputing application, solving a partial differential equation, you have a large amount of local computation with good locality. You're computing on nodes that are right next to each other. You have to do relatively little communication, and it's localized, so it's easy to map onto a large machine. And then occasionally some small global reductions. And you can statically or nearly statically get good load balancing local communication. On the other hand, if we look at an example graph application like breadth first search, the pattern is very different. You have relatively little computation, no floating point at all, but random communication because many of the graphs that you deal with in applications are either impossible or impractical to partition well. And so you get random communication, low locality, quite likely poorly balanced load. And so if you walk through the breadth first search, you start with this vertex A, and then you explore its outgoing edges, and that gives you B, C, and D. And then you explore their outgoing edges to get the rest. And notice how many of these edges cross between processors represented by different colors here. And this is very much like many of the data-driven applications that we have to deal with. And so if you look at traditional scientific applications versus data-driven ones, you start with traditional applications that are coarse-grained versus very fine-grained dependencies, single-element computations in data-driven applications. Traditional scientific applications tend to be static or nearly static. Even when you're looking at things like evolving meshes like the talk earlier this morning, or mesh refinement on the mesh, that you still have relatively small change and relatively localized changes. On the other hand, many of these data-driven applications have dynamic topology structures. You also have good load balancing on traditional applications versus poor on these new applications. And you end up having communication that's bandwidth bound with large messages. You can stick things together into large buffers, send them as a unit, and that's what supercomputers are designed to deal with well. On the other hand, these data-driven applications tend to be latency or throughput bound with many small messages going to random places. And so overheads like network packet headers become a problem. And then overall, traditional scientific applications communicate data. Well, these new applications communicate control flow. You're saying this is the next vertex to process, tell this vertex to do its computation and send down to its neighbors. And so one approach that's become more popular recently for handling these sorts of problems is active messages. They were invented in 1992 for split C. And in this model, messages are sent explicitly, but receivers register message handlers and aren't involved with individual messages. You just put in a handler that says, when a message of this type arrives, call this piece of code. So there's explicit sends but implicit receives. And so in many of these models, messages are asynchronous to get higher throughput. So you have very much a fire and forget model. You can blast out a whole lot of messages and then there's some other synchronization mechanism that determines when they're done, but you don't wait for individual messages. And so the reason that these are good for these data-dependent, data-driven problems is that they're highly asynchronous. You have implicit communication on the receiver, so the receiver doesn't have to say block until it gets data. You have less waiting for nodes to reach the same location. You have a lot fewer global reductions, barriers. You can do multiple, on fancier algorithms that are not as work efficient, you can do the entire breadth first search with only one big global synchronization at the end. You do some extra work there, but then it becomes fully asynchronous. And you're often able to send messages in the background while computation continues on some other task. And unlike a PGAS model, remote direct memory access, or these sorts of remote update memory access models, you can have compound operations in one message. So for example, you can have an operation like check the color map for a given vertex. If that color map entry is marked as white, then you set it to black and push the vertex into the queue. And that's something that's very difficult to do with compare and swap, and in weak memory consistency models requires a lot of extra synchronization. And so our variation on generalized active messages designed for graph and irregular applications is called Active Pebbles. Active Pebbles is a programming and execution model that's designed to allow the natural expression of these fine-grained applications while still running efficiently on large machines. And so here at the user side, you don't have to coarsen your applications artificially. You can send individual tiny messages to tiny objects, and the execution model takes care of that. Now, because many of these applications are sending so many tiny messages, there are many places where you have to trade off latency for throughput. And I'll show you how that happens later. And our implementation of that is named AM++, and it's in C++. So in the Active Pebbles programming model, you can program applications with their natural granularities. And you can have transparent addressing of local and remote objects, which we refer to as targets. And so a target can be, say, a single vertex in a graph. You don't have to do any sort of pre-processing to talk to a particular vertex or have some particular structure in objects that are callable remotely. Data distributions are completely user-defined. They're just an arbitrary function that maps from an object ID of whatever form to a location. And so they can either be static or dynamic. For many of the applications we're concerned about, since partitioning is so inefficient, we tend to use static distributions, like simple ones like cyclic, because they're much faster to deal with for large message volumes. And things like sending messages to yourself are detected automatically. You don't have to incorporate that into your algorithm. And then there's an epoch model that's set that enforces global synchronization when you need it by making sure that all messages have been sent, they've been received, they've been handled, and any messages that are sent by those message handlers have themselves been received and handled. Now, the execution model that makes this efficient uses four main techniques. The first one, which is fairly standard, is message coalescing. And the goal of that is to amortize things like network packet overheads. Of course, that hurts latency, and it also takes up memory. Another thing that we're able to do is message reductions to eliminate redundant computation and communication. So for example, in a breadth first search, if you're sending two update messages to the same vertex, the second one is completely redundant. And therefore, we employ small and very fast caches on local nodes to detect these duplicate messages in some cases and then prevent them from being sent. This also allows distributing computation into the network. So for example, you can have many sum updates to the same node reduced partly locally, sort of like combiners and MapReduce. We also employ active routing to reduce the number of coalescing buffers that are needed at large scale. And also this allows the caches to become more effective because all of a sudden you can now remove duplicates across multiple sources that happen to use the same intermediate hop. And finally, in order to detect in the presence of recursive message sends when the entire system has quiesced, we use standard termination detection algorithms from the literature. Now, just to show an example of this, this is what breadth-first search looks like in an abstracted active message model. You start off with your, and this is a level synchronized implementation. So you're going to do one level at a time with a global barrier between levels. And so so you have two queues, you have an input and an output, and then you swap them after each level. So the first thing you do is have a loop until there are no more vertices left. You start off with an empty queue and then swap it at the end. Now the next thing you do is start an active message epoch. And so this adds the synchronization at the end. And now all you do is walk through the vertices in the input queue and then through their neighbors. Now the problem is that these neighbors might be remote. And so that's not going to be something you can handle just on this node. And so therefore we have to send a message to the remote node. And we're going to tell the owner of that vertex to run the vertex handler. Now, what is the vertex handler? That tell sends messages to the vertex handler. And now this vertex handler does the body of the loop. It tests the color map, and then updates it if necessary, and appends to the new queue. And so then we have to register that handler, and note that that handler is a closure. It has member variables that represent state that are references to variables in the main program. And then the problem is here, or one of the main issue here, is that notice that there's this barrier. There's this line in between writing the algorithm in one place and writing the handler in another place. And so this tangles the expression of the control flow in your program. And there are other examples that have more nested communication, where you effectively end up writing the program backwards. Because you're writing sends, and then the handler is above that. That handler sends to something else, and so on. And so in order to deal with these issues, we've created the Avalanche system, which is a distributed data flow graph framework on top of active Pebbles. Now, this is loosely inspired by TBB Flow, and you'll notice some of the names will be similar. But it's very different in terms of the semantics, in that here graphs are mostly specified at compile time. And it supports distributed memory with explicit data redistribution. And all of the active Pebbles, the user-defined data distributions, routing, reductions, and so on can be used. And the implementation is written in C++ 11 to simplify the code. And so to take advantage of the type system improvements and things in that language. And so if you look at a very simple flow graph that's doing a permutation and then writing into a distributed array, you send the input array, redistribute it by the owner for the permutation, do a local lookup in the permutation, redistribute now based on the result, the addresses that come out of the permutation, redistribute to the final locations, and then finally store in the output array. And so the overall approach is that you would write your application kernel as a data flow graph built using combinators in the form of C++ function calls. The flow graph is run in a SPMD style. The exact same flow graph is run on every node in your system, and then it's the data that varies. And when I show dynamic flow graphs, those can also vary across nodes. Execution here is for performance reasons to avoid synchronization. Execution is interleaved within a single thread on each rank, and I'll talk about why later. There are other models that could be added later. And communication is explicit using redistribute nodes. And so the goal, just like for active Pebbles, is very high performance on huge numbers of tiny messages. And so we're assuming little computation per input. And therefore we can't afford things like dynamic work stealing schedulers and things. We need to do, we're actually at the point where we're inlining function calls for we're inlining flow graph node bodies into each other, so they don't even become separate function calls. And so if you look at a diagram, you have a flow graph replicated across all the nodes, and everything is local except for the redistribute node in green. And so all the connections between local nodes are local function calls, and as I'll show later, we've set up the system so that those can likely be inlined by the compiler. Now, the green node is a redistribute node. It's the only type that does communication. And so it can do an all-to-all communication using the active Pebbles implementation. And so in the flow graphs, the main abstraction is a single input, single output node, and there are special cases for the beginning and end of the pipeline. A node is a C++ object with a defined interface. And now this interface is not in the sense of an object-oriented interface. It's effectively a concept. It requires certain functions, some of which are polymorphic. And so we are actually using higher rank polymorphism here. So there are combinators that build nodes from functions to build these function nodes and other nodes. And the structure is mostly set at compile time, but can be plugged in at runtime as well. Nodes can be polymorphic in their input type, which is mostly a convenience feature for users. And so you start off with a raw node, then you compute its output type based on the input type, get an intermediate state, and then you plug in the continuation for the next node to get a bound node. And so each node in the final, after it's been fully instantiated, is effectively a function that represents what to do when you pass an element to that node. And then these functions are composed for pipelines, broadcasts, and so on. And usually we use the type system to ensure that the function bodies are known statically, avoiding dynamic dispatch and taking full advantage of compiler optimizations. And so if you look at this simple pipeline, you walk backwards through the pipeline, taking the continuation of the successor. Now, the first thing you do is compose N2 on top of it. And that wraps N2's continuation so that when N2 is done processing a message, it might send 0 or more messages on to the continuation of the whole graph. Then we do a similar thing for N1. And so you get a combined continuation that represents the entire pipeline. Now, even though the code is in C++, I'm going to use Haskell and Haskell-like notation for pseudocode because it's easier to explain, is much more concise and allows the expression of things like type classes that don't exist in C++, that equivalents don't exist in C++ right now. But actually, as I'll show later, some of the things that I'm doing are doing such fancy type tricks they can't be represented in Haskell either. And so at the basic level, you define a type that represents a continuation, which is just a side-effecting function that takes an object of type T. And then a pipeline from type I to type O is a function that takes a continuation for O and returns a continuation for I. The thing is, especially in C++, this restricts the compiler's, writing it naively like this, restricts the compiler's ability to do things like specialization based on the exact function used in the continuation. And therefore, that harms the ability to do inlining unless you have a much more sophisticated compiler. And so the first step here is to make pipelines separate types. And so rather than a pipeline just being a function with a certain interface, you have a type class that represents a pipeline. And so then it has a compose operation, which now can be computed from the type of the pipeline object, rather than just its value. But still, this provides a way to convert to ordinary functions, and the bodies of the functions are not known until runtime. And so the final technique that's used to lift this, to make the compiler much more aware of what's going on, is to also make each function body a separate type. And this is similar to the defunctionalization that Milton does, and is a standard technique in C++ for using function objects and getting high performance out of standard compilers. And so here we first define a unary function, which is a function, is a type representing the function itself. And so the values of that type would be closures with a certain body, and then take the input type and then can be applied. And now, since this is pseudocode, we can have polymorphic superclass constraints, which don't exist in Haskell right now. And so what this is saying is that a pipeline has to be able to take an arbitrary function from its output type, and the function's type is nx, and it has to give some composed type that takes the input type as argument. And so this composed is likely to be a new type that the user will create, which encapsulates the body of the composed continuation. And so even though this code is much nastier, it achieves much more optimization because C++ compilers specialize polymorphic functions and classes based on their input or type arguments. And so this gives you a full access to that specialization. Now, as we go through the node types, the most primitive one is the CPS function node, which just takes a function object, which might have mutable state since this is C++, and converts it into a flow graph node. And the reason it's done using continuation passing style is so that a node can return 0 or more outputs for a single input by calling its continuation multiple times. And now, unfortunately, these function nodes can't be lambdas in C++ 11 because lambdas are only monomorphic, and you don't know the type of the continuation up front. And so you end up writing a class like this that has CPS result type, and then an operator that takes a continuation and an argument does something, which might call the continuation. And then there are wrappers for single output functions so that you don't have to deal with that composition of the continuations. There's a wrapper for filters that either return 0 or 1 result, and so on, and then different nodes for the beginning and end of the pipeline. Now you also have a pipeline combinator which just concatenates two nodes, composing the input and output types. And because of all the weird type tricks, it allows the body of the second node to be inlined into the first node whenever it's small enough. Now the only node that does communication is the redistribute node, which gives you all of the active Pebbles features. And then those are controlled by a message configuration object. And the reason that that's done is to allow modularity for user-defined generic code, where you have a library writer who defines the semantics of their messages, and then a caller or some tuning system that supplies how it's going to be done based on the message semantics. And so that right-hand side can be tuned for individual hardware use cases, etc., without having to change the algorithm that's on the left side. And then again, the destination is given by an arbitrary user-defined data distribution. Now we have a couple of utility node types. So for example, we can have a loop node set up at compile time. We can have a subgraph, which is an internal flow graph that's run independently with its own synchronization and then returns a value at the end. And then a broadcast merge so that you can do things like fork join operations, send the same input to multiple sub-pipelines, and combine the results. And then just with the nodes that I've described so far, you can build a fork join combinator that assigns IDs to input elements, spawns them off to different nodes, and then merges the results, sticking them back together into a tuple. And that can all be done without mucking with the internals of the library. We also support dynamic flow graphs, and so unlike the compile time flow graphs, you lose some performance, but you have dynamic sender and dynamic receiver, and you have an add edge function to compose them at runtime. Now there's a small performance penalty because you don't get the inlining, and it would be easy to add a wider variety of these. Now I mentioned threading before, that we just run all of the nodes in a single thread. And there are other ways to do that. The core of Avalanche is thread safe, basically because it has no or almost no shared data. Parts of fork join are not, but that's just an implementation limitation. And so we could instead run multiple AM++ processes per system process, or special node types that say will fork their successor as a task for each input in some sort of work stealing system like TBB, or have a threaded fork join model. So just to briefly go through an example, since I'm getting near the end of my time. Here's an example of a breadth first search written in the actual code versus its flow graph. And so you see here as you walk through that the nodes correspond very directly to the sections of the code. The subgraph block goes to a subgraph function call. Iterate container goes to iterate container. And that actually also returns the size of the queue, which is used later. The function for getting outgoing edges, and so on. And so you very directly can express the flow graph as a series of function calls. And so performance here I'm going to show just relative to AM++. So this is run on a BlueJean P on up to 512 nodes, one process per node, single thread. And so you can see that there ends up being about a 7% performance loss of Avalanche compared to AM++. And that seems to be from limitations in the compiler, where it's not able to optimize out all the indirections it needs to match hand-tuned code. Now, I'm not sure why AM++ is slower here, but that's not something that's related to Avalanche. Now, there are several opportunities for future work. One would be to port it to another language, do some more functional language like Haskell, where the GHC optimizer might very well be able to do the level of specialization that's necessary to make a much simpler implementation. We could also target some other backend like Charm++ instead of active Pebbles. And also, because of these compiler limitations, it might be useful to have compiler assistance. And so specialized optimization, specialized code generation, and so on. And of course, we can lift this to cover other declarative approaches for irregular applications in general. Thank you.
Questions? I have one. You mentioned that you have single-threaded nodes, or single input, single output. Did you try single input, multiple output, or multiplicity at one of the ends of the node?
So I have this broadcast merge combinator that takes a single input and pipes it out to multiple subpipelines combining the results. And so you can have nodes that have multiple outputs and multiple inputs. And that would be the type of structure that would create that.
So you hide the multiplicity in the pipe system, if I understand correctly?
Well,
because I haven't seen threads and threaded things.
Right, I haven't shown threads here, but these continuation functions can easily be spawned in their own threads or tasks or whatever in a work stealing system.
And are the nodes buffered?
No, it's strictly a CSP model, and that's to get performance. So immediately when a node outputs something, its successor's continuation function is called on that output, and so on, possibly around loops and such.
You had an architecture where AM++ active Pebbles is in charge of doing the shared memory-based routing, right?
Mm-hmm.
One would hope that from an application point of view, is that having the communication infrastructure, the communication basically done at a level that it does not require shared memory or non-shared memory, any of those things, but you seem to have separated it into separate layers, right? The top layer is API.
Right, because this is originally targeting purely distributed memory. And so therefore, if you program it as if it's distributed memory, then it'll run in shared memory just fine. And of course, you can run MPI in shared memory right now. The shared memory transport is to allow things like ownership passing of buffers and other things that are only possible in shared memory and not using message passing at the system level.
So my basic question was whether active Pebbles is a good infrastructure for all kinds of levels of memory, distributed and shared, or whether it favors, whether it has some built-in favoring of some assumptions about, you know, like shared memory or non-shared memory.
Well, I think it's good in general. The thing is, because you might want to use very different communication structures like no coalescing and shared memory, you might want to have some tweaks to the implementation to more directly address shared memory to get better performance. You know, to take advantage of certain things that you can only do with shared memory and not in a real distributed system.
Let's thank the speaker again.